Sup guys, today we are gonna continue coding on our binary tree. We are going to create a pretty printer function which prints out the tree in a graphical kind of ASCII way. So it will be easier to understand how the tree is constructed, and it will also be easier to troubleshoot if we have to. Let's get to it. But first we need to add a couple of other things into our tree. So this is what we have this far when we run it. We create an example tree and we grab some values from it. And these are the addresses to the nodes. So what do we have this far? Well, we have a couple of functions. This is the first node, by the way, of the tree. It's statically defined and it's the root of the tree. Then we have the 0 function, which simply memsets to 0, a variable. And we have create node, which creates a node of our tree. So basically it will be like a folder containing the actual data structures. And here is a find the last leaf, and it's a linear version of it. And we do also have a function to create a leaf, and the leaves are containing the data. So every leaf will contain one string, basically, of any size. And that's basically what we have. And inside of the main we have a couple of example stuff, which will not be here when we are done with the code. So where do we begin? I think it will be useful to have a function which prints the tree. That will make it easier to grasp how everything is working, and it will also be easier to troubleshoot if we get into any errors. So that we will create, but before that I want to create all the function declarations, because I never did that previously. So let's just let's do it like this. So we have the 0. So void 0, and we have an int pointer and an int 16. So we have an int 8 pointer and an int 16, like so. And the next thing is create node, which will return a node. So we have our node, create node, and the arguments. We have a node as a parent, and we have a string as a path. So node like this, and an int pointer as a string, like so. Then we have the linear find last leaf, which will return a leaf pointer, find last linear, and we need a node. And finally we have this create leaf function, which does also return a leaf. So So create leaf, and what do we give it? Here we do have a couple of arguments. We give it a parent and a string. So a node and an int 8 pointer, and then we have an int 8 pointer as the value. And finally we have an int 16 counter. So int 16 like this. And at the moment we do also have a main. Do we have arguments? No. Okay, let's see if we did this right and it still compiles. Yes. And the same results as before. Okay, so now we have a little bit better structure. So let's create this printing function. And in order to create that function, we need a couple of helper functions. One being an indentation function. So basically we need to create a function which takes in an integer as an argument. So let's it will be called like this, indent, and let's say we provide it with the number 4. Then this should return a string with 1, 2, 3, 4 spaces. Or no, let's do it like this instead. Let's say we indent 2 steps, and each step being 2 spaces. So if we give it a 2, it will return 4 spaces. I think that's better. So let's begin by the function declaration so we don't forget it. So this will return an int 8 pointer, a string basically, and it's indent, and it takes in an int 8. Like so. So it'll be int 8, let's see, indent, int 16, what should we call this? Let's just call it n. So that's the number of indents. So how can we do this in a practical way? First of all, we need some kind of a buffer, which we will write to. So let's create an int 8 buffer of size 256. So this we will fill with the data. We will probably also need a pointer. So let's start out by zeroing out this buffer, like so, and we need to have some kind of check to double check that this parameter is not too big or too small. So how big can it be? Or should it be? We have 256 as a maximum amount, and each space is in 2 spaces, which makes it 128. And then we will have a 0 byte at the end. So let's do the maximum for 120 just for the sake of it. So we can rely on assert in this case because, well, as a programmer we shouldn't give a function bad arguments. So what do we assert? We assert that n needs to be bigger than 0 and that n needs to be less than 120. Right? So let's do a for loop. And we need some kind of counter as well, by the way. Let's call it I. So we begin by setting I to 0, and we set p equal to buff. So it points to the first part of the buffer. And we are gonna iterate as long as I is less than n. And each iteration what will we do? Well, for starters, we're gonna increase I by, by 1. And are we also going to increase p right here? Well, let's do that. So p plus equals 2. So we will jump 2 steps at a time. And at each step, we will simply string copy to the position of p. We need to do this. P. And what are we going to string copy into it? We will do the string of 2 spaces. Maximum 2. Like so. Let me just double check one thing. So we have, from the beginning we have nothing, then we string copy 2 into it, and then the pointer starts here, and we move 2 steps to the right, and then we string copy to this position, 2 spaces. I think this is correct. And at the end we will simply return the buff. But that buff is currently on the let me just remove this. The buffer is currently on the local stack of this function, so we can't really return it like this. We can malloc it, but the way I'm going to use this function is iterate a lot of times, so I don't want to have to free all these memory allocations. So let's do this as a static buffer instead. Static basically means that it will be accessible outside of this function, and it will keep its current content, but we will zero it out every time, so that shouldn't be a problem. Let's go towards the end of this function inside the beginning of our main, and let's just try it out. So we will do a printf, and let's say we print something like int main, and a new line, and after that we put in an indentation and return 0, and an ending bracket like this. And what will we send to this printf? We will do indent 2. And then we are going to, let's do like this, and this, and this. And let's call this something else, func. And this, we will do, no, 1 here and 2 here. That'll be good. And then we will simply return 0. So this is a temporary thing, of course. And let's recompile. Oops, what did we do now? Conflicting types. Int 8, indent, int 8. Oh, I did an int 16. Well, we're not gonna be needing that kind of many characters. Let's do this in int 8 instead, like so. And we jump down a little bit, we run make, and now what? String copy output truncated. Oh, I really do not like this annoying warning, because this is basically for people who don't have a clue how the memory works. Because this is a totally safe operation, and it's not even warning us that we can overflow the stuff. It's basically warning us that we might not overflow it. It's kind of bizarre, but I think I'm gonna remove these kinds of warnings actually. So let's see where I have that kind of code. So let's do cat of something like code OOP and lambda.h. Here we go. I never remember this pragma stuff. Perhaps I should not copy paste it. I should write it instead so I can remember it. So pragma GCC diagnostic ignored. I'll put it almost at the top of this H file. So pragma, what was it? GCC diagnostic ignored. So GCC diagnostic ignored, right? Weird English. And this is the error warning message that we want to suppress. So let's just put it right here, like so. And then we will have another pragma, GCC diagnostic diagnostic, tough word to spell, diagnostic push. And if we have a push operation, we will also have a pop operation, and let's put it at the end of our C file. So pragma gcc diagnostic pop, like so. And let's make clean and make. There we go. Okay, so let's test this. Yeah, it seems to work. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Okay, so now that we have our indentation function, we can begin coding on our pretty printer, which will print our tree to the console or to any file descriptor. So I'm thinking something like this. Let it be a void function, print tree, and the first argument is a regular file descriptor, so we can tell it to print it to the standard output, for example, or we can print to a file. Second argument is the starting point, the root of the tree. So it can be the actual root, or it can be some other part where we want to start traversing the tree structure. So this is it's a tree of type, let's see, of name, let's call it root with an underscore. And what else? That ought to be enough, right? So before we do much of anything, I want to create the function declaration so we don't forget that. So we are below here, and this is a void print tree, which takes a regular int and a pointer to a tree, like so. Alright, so how do we do this? We need to have two for loops where we iterate through the tree structure with one of them, and if we find any leaves connected to that node, we will traverse that as well, while printing everything as well. So let's start by defining an int8 indentation, and we need to have a node n and a leaf l, like so. And let's see, we need some kind of a buffer as well, some intermediate structure that we can use before we print to the screen. So let's do int 8 for consistency. So buff 256. And we do also need a size t. So an integer which we'll use to calculate the length of the string. But let's do int 16 for that. So we'll call this size. And now we probably have what we need. So the first loop, we will set the n, which is a node, and what we have as a root is a tree. So we need to convert this to a node. So n equals the underscore root. That's our starting point. And for how long are we going to loop? We're going to loop as long as, let's see, as long as n, what's it called? And west is the downwards facing point. So if this is 0, then we're done. So as long as n west is positive, and we will set n equal to n west at each iteration. And what we're going to do when we get to this point, we will craft the beginning of our buffer. So let's see, we can use string copy. First I want to zero it out, by the way. So let's do 0 buff 256. And then we string copy into this buff. So we need to convert it to a char. And what is the first we want to put in here? So let's see. We also need to set the, let's do it above, the starting point of the indentation. So let's set it to 0 at the start, and let's modify our where is it? Our indentation function a little bit, because currently we check that n is greater than 0. I think it will be easier if we allow it to be 0. So let's remove this definitive restriction, and instead we'll check the first thing we do, that if n is less than 0, then we set n equal to, no, let's do this. If n is less than 1, then we simply return an empty string. And we need to encode it as int8 pointer. But that must be the best way of solving this. So if it's less than 1, then we just give back an empty string and assert that n is less than 120. Yeah, that's correct. Okay, so where were we? Up here. So we set indentation to 0, and then we can simply string copy into the buffer our indent function with our indentation. Because if it is 0, which it is from the start, then we will simply return an empty string, and this will try to copy an empty string, which will result in a no operation. So that's all fine and well. So let's see, we have created the indentation. Let's calculate its length. So size equal to, and we want the int16 representation of string length, and to string length we send the char representation of our buffer, and this should result in 0 at the first run. And let's just do if size is not 0, then we write to the file descriptor the char version of the buffer with the size. So this is our way of printing out the stuff. We will string copy, we will zero it out, string copy, calculate the size. If the size is positive, we will write to the FD. Okay, so let's continue with our print tree function. Since we are using the same 1, 2, 3, 4, 5 lines every time we want to print something to the screen, let's factor out this into a macro, right? So let's go to the .ah file and find a suitable place for the macros. Let's do it right here, and we paste this, and let's see. Okay, so that didn't work. Let's keep this indentation. Okay, so what do we want to call this stuff? Let's say something like print, maybe. And we're gonna have a couple of arguments, right? So what do we have here? 0 the buff, that would be the same. Then we have the string copy to the buff. This indentation will change. So let's put an X here. And then we remove this stuff. And we just put X there. And you don't really need the parentheses, but it's good to always use parentheses when you refer to this argument, because in some instances it will be necessary. Okay, then we calculate the size depending on the buffer. That will be the same. We double check that the size is what it is, And then we write to the file descriptor. That would be the same. The buffer, the size. The only thing changing is this X. And since this is a macro, we will have to put this slash at the end of the lines. No, not curly braces, slash. Slash. But not on the last line, and we don't need this semicolon at the end either. So let's save this file, and then we can simply remove all this, right? And instead we can simply put print indentation. No, the function is called indent, but the argument is called indentation. And then we do like this. And we also have to increase the indentation. So let's just put plus plus right here. So the first round it will be 0, and then it will auto increment right here. Okay, so now we have printed the indentation to the screen. What else do we want to print to the screen? Well, we are in the first node, so we should print the path of the node. So let's see what we have. We have it's called path. So then we can just copy this line and paste it like this, and we remove everything inside of here, and then we just type, let's see, we have n for the node, and then path, like this. Alright, so these macros are really helping us when we need to repeat stuff. Okay, what's the next step? Now that we have printed out this stuff, I do also want to print out a new line, like so. And now we can get to the actual leaves. So let's do let's see. First we need to check if there actually are any leaves at all at this node. So let's simply do if n has any nodes, and what is it called? Let's see. The nodes, the leaves, the leaves are connected to the eastern link. So if n east is non-zero, then we want to do another for loop. And this time we will take the L equal to n east. And what do we want to have as a condition for this loop? Well, it will look kind of the same as above. We want to check that the leaf and that it has something to the east as well. So if it has something to the east, then we go on looping. And let's see if it has something to the east. So if it does not have something to the east, it will not run at all, right? So maybe we should simply do L here instead. So if we have L, and each iteration L equals L west, like so. So we set it to the east, and if we have something there, this will be true, and then we do this. What about the nodes? Did I think correctly there? So if we have this node, let's see, we check that if we have anything to the east, west even, but if we don't, we still want to process this root. So let's do like we did with the leaves instead. So n equals node root if n is true. Let's try this. Okay, so what are we going to do with this loop then? Let me just put this at the end instead, like so. So basically here we want to do the same as we would with the indentation, with the path, and so on. So let's see. We first want to print the indentation, but the indentation has it changed? Yes, it has changed. Okay, perfect. Then we can simply do print, and we do indent according to indentation, like so. And after the indentation, we want to print the let's see what it's called. We have the key and the value. The key and the value. So basically, we want to print, let's see, we want to print the node's path and add to it the key. I think that would be the best. So let's print n path again, and then we print I don't remember if this ends in a backslash. I don't think so. Well, that'll we see. So for the sake of it, let's front slash, let's print one of those as well. Then we want to print the key of the leaf, so L key. Then we want to print, let's see, a space and some kind of arrow perhaps. And then let's do single quote, so we can show the value in a good looking kind of way. Then we have the L value, but that we need to do a little bit differently, I think. Yeah. That's right. I think we need to do it manually this time. So we write to the FD. And why do we need to do this manually only here? Because we don't know firsthand that this how big this value is, and we don't know, but it's not zero terminated, not necessarily anyway. But we have the size here, so we can use that directly instead. So we just print to the FD the L value, and we give L size as an argument. And perhaps we need to turn this into a char and this into an int, maybe. Something like this. And then at the end we want to print out, let's see, it'll be a single quote and a new line, right? I hope I'm getting this right. Something like this. And then I'll just put a return at the end like this. And are all these lining up? This is a for loop, and this blue thing is this for loop, and then we have the if condition. Okay, so let's save this, and let's go to the end of the file, and inside of this main, where we have some things already, let's see, let's remove this one. I don't have my key bindings right here. Well, let's do it manually. Like so. And do we have any additional print? F, we do. Let's remove that. And we do already have an, okay, this we need to remove too. Like so. And we have a tree here already, a small example tree. So before we free that variables, memory allocations, let's just do print tree and root like this, I think. Let's see what happens. We probably need to do some troubleshooting in this case. It's a lot of moving parts, right? So this, and let's do make clean. Jump down a little bit, clear the screen, and we run make. Boom. Okay. And as usual, I think most of these are have one cause. So let's see, on line 21, pointer targets in passing argument 2 of string copy differ in signedness. Okay. And it's inside of our macro, right? So what does differ in signedness mean? Well, you can have a variable signed or unsigned, and the signedness is basically that possibility of a minus sign. So if it's a signed variable, you can have negative numbers, and in an unsigned, you don't. So this has to do with my own integers. I have int 8, int 16, int 32, and so on. So that's why I need to cast so much. And let's do that in this instance too, because this will always be a char pointer. So let's just do this, and that should be it for that error. So let's jump down, make clean. We don't really need to do make clean every time though. Make, okay, that's quite a lot less. So let's see, warning assignment to leaf from incompatible pointer type. And what is that? L equals L west. So how did I define L and L west? Let's see, where is that? The second is this one, L west, is a tree, right? That can be both a node and a leaf, but we shouldn't really target that in this case. So that's probably what's wrong. L west. Let's see, we need to go to the right, and to the right is east, like this. And N is also east in this case, and if N east, but here it should be west, because to the west we have all the nodes linking up, and to the east we have the leaves. Okay, let's try it again. So let's see, we jump down and we run make. Alright, not many left this time. So what is this kind of, oh, that must be a typo, right? 159. So 159. Yeah. Okay, let's see if it compiles now. No, now we got a couple of other errors. Argument 1 of print tree makes integer from pointer without a cast. Right, we need to cast that one, because that is a tree and we are treating it as a node. So let's see, go here, and I accidentally closed that file. There we go. So let's see, print tree, it wants a node, I think. Let's check the signatures. Print tree, no, it accepts a tree. Oh, but it wants an int as well. Right, that's the one. So we need to put the FD. And what is the FD for standard output? Well, you can think like this. First is the input with the keyboard, so that's 0, and then we have the standard out, and then we have the standard R. So in this case it's simply the 1, like so, and we go back and we compile, and we are compiled. Very nice. But let's see if this actually works. So let's start this up, And what did we call it? Simply called it tree. Okay, now we're talking. So we have the root, then we have the users, we have the users login, and inside of users login we have a leaf called job, and if we check the contents of that key, we get this string, and it looks kind of random, but if we go to the code and we check what we did put in that, we have this, right? So it works. But what about me? I was left out. Why is that? Okay, so let's try something different. What if we begin at the last leaf on the branch and we travel to the left instead? So if we set L to, let's see, we do have a function called find last, and I think we only need to give this a starting point. Let's check the signature. So it's an alias for this, find last linear, and it takes a node. So we give it L, and we loop as long as L, let's see, as long as L west, let me think. Let's move this down a little bit. So what if we were to loop until L west is not 0? When is L west not 0? Then we are at the node, right? Let's try comparing this L west. If this is not equal to the N. Yeah, we need to try something, right? And at each iteration we go to the west instead, until we've traveled to the last leaf before the node, right? So let's check if this works. Let's recompile this stuff. Okay, what is it saying? Comparison of distinct pointer types lacks a cast, but that shouldn't be needed, right? Because it's a tree. Okay, so let's go to the code and let's compare. Let's see, L west. This is a tree and this is a node. So let's turn this into a node instead, like so. And we make clean, we jump down a little bit, we clear, and we try again. Okay, that's better. So what is it saying now? Assignment to leaf from incompatible pointer type. Okay, it's the same thing there, I guess. So let's see. L equals L west, and this is a tree. So this should be cast as a leaf. think this is the best solution. Let's see what happens. We do make clean, jump down a little bit, we run it, no warnings, and it's segfault. Okay, so now I think I know why it's segfault. If we look right here, let's see, we set L to find last, but if there are no leaves, it will not find anything, and it will return 0. So that is making this crash. We need to create a variable instead. So let's create another leaf pointer and let's call it last. And let's add those so we can do, let's see, we will set last equal to find last of n, like this, and let me add this ending bracket as well so I don't forget it. And what else? Then we will replace this part. Let's see, we will do something like this. We will set it equal to last, but first we need to check if last is not 0, then we do all of this, right? So let's see, where does it end? There, like so. This should work, right? And this find last is most probably the initial error as well. So if we go to last, find last, let's see, find last linear. It's an alias for this one, right? And if the parent doesn't have any leaves connected to it, then we use our return error function to indicate that. But this does not return 0, right? If we go to the H file and check this ret error function, or macro rather, it sets the error number to 0 in this case, and then it returns the null pointer. The null pointer is set to 0, but it's an intermediate step, right? So that's why it's not working properly. Let's make our lives easier and just return a leaf version of 0, like so. Save this one, we go to our code, and this is how it should look like. We are pretty printing our binary tree. We have the root, and then we have this folder and this folder, and inside of this folder we have Lucy and the value of Lucy. We have John and the value of John. So now it's working. There are a lot of interesting things coming forward. So next week I will do the second episode of our anti-denial of service tool, and we will also later on continue to this binary tree and add the hash table algorithm, so we have a more optimized way of searching the tree. And there will also be a live stream. I'm not exactly sure when, but soon. And then we will continue to create our in-memory database. So a lot of interesting things coming up. And if you like this video, please subscribe or give it a like. And thanks for watching, and thanks for today.